Hello, in today's video we're going to be talking about parent functions and transformations. We're going to focus on four parent functions. The first is a constant function. Remember, f of x just means y, so really we're looking at y is equal to 1 in this scenario. If I draw my coordinate plane, y is equal to 1 would be a graph that is a horizontal line, something like this. A linear function is y equals x, or f of x equals x, and that would be a line that passes through the origin and has a slope of 1. Absolute value is very similar to a linear function, except any negative values bounce up to be positive. So the positive x values remain positive, just like they did in the linear function, but that section on the bottom left is going to bounce up and become positive y values. So our absolute value function is a v-shaped graph. Quadratic has the form y equals x squared, and that is a u-shaped graph with a vertex at the origin. In the four graphs below, we're going to identify which family each of these belong to. Now there have been some transformations. They have been maybe moved somewhere or flipped over or stretched a little bit, but the basic function family will narrow down to one of these four. So the first one has that u shape of a quadratic, so this is going to be a quadratic function with the equation y is equal to x squared. There's more to obtaining this specific graph, but the parent function boils down to x squared. The second one is a line that is not horizontal, which would make it a linear function, y equals x, and the name is linear. A v-shaped graph is an absolute value. We are bouncing back up after we hit 0. So that would have the form y equals absolute value of x. And then lastly, I do have another u-shaped graph, which would make this yet again another quadratic with the form y equals x squared. What we're going to look at today is how do we take the parent function and obtain graphs like these from that home base parent function. Looking at each of these equations, we have some adding, subtracting, multiplying, and dividing, but what we want to do is see, despite the different operations, adding, subtracting, multiplying, and dividing, which of the parent functions do these boil down to? This first one, for example, y equals 12 plus x, we ignore any adding, subtracting, multiplying, or dividing, and we see that this is the function y is equal to x. So that would be a linear function of the form y is equal to x. So if I were to sketch a quick graph, it would be a line through the origin with a slope of 1. The second one, I'm going to ignore any adding or subtracting and multiplying or dividing. This negative is considered multiplying. Essentially, it's a negative 1 times the absolute value of x. So we ignore that as well, and we see that this boils down to the absolute value of x. So this would be an absolute value function with the form y is equal to the absolute value of x. So to sketch a quick graph, I would have a v-shaped graph centered at the origin. Number 5, I ignore any adding, subtracting, multiplying, which would be this 5, and dividing, and that leaves us with just absolute value. Or y is equal to the absolute value of x. To sketch the graph again, I have a v-shaped graph centered at the origin. Second row, I ignore any adding, subtracting, multiplying, or dividing, and I see that we're left with just the absolute value again. So this is yet again another absolute value with a parent function y is equal to the absolute value of x. Sketching, I've got a v-shaped graph centered at the origin. Here I ignore any adding or subtracting and any multiplying or dividing, and I'm left with just y is equal to x. So this would be a linear function. Y is equal to x, and that's going to look a lot like the very first one. We have a diagonal line with a slope of 1 going through the origin. Ignoring any adding, subtracting, multiplying, or dividing, I'm left with x squared, which would be a quadratic function. Y is equal to x squared. Sketching a quick graph, I've got a U-shaped graph with the vertex at the origin. Ignoring any adding, subtracting, multiplying, or dividing, here is the addition and subtraction that I want to ignore. What we're going to focus on is the higher of the exponents. So this is what we start with, and we ignore anything extra. So I'm ignoring the minus and the 3x, and that leaves me with the 6x squared. So adding, subtracting, and then also the multiplying, so we ignore the 6, and it all boils down to x squared again, which is another quadratic. Y is equal to x squared, which would be a parabola or a U-shaped graph centered at the origin. Adding and subtracting, I ignore the 5. Multiplying and dividing, I ignore the negative. And I'm left with y is equal to x squared, which is another quadratic. U-shaped graph centered at the origin. Lastly, y is equal to x. That's the exact form of a linear equation. So the parent function is y equals x. This is the parent function. We didn't make any changes to it. We have a line through the origin with a slope of 1. On the next slide, you're going to have the opportunity to practice 9 of these on your own. Go ahead and take a moment, pause the video, and practice these 9. Number 1, we should have a linear function, which would be y is equal to x, and the graph would be a slope of 1 through the origin. Second would be quadratic, y equals x squared, with a parabola centered at the origin. We have another quadratic for our third one. Parent function is y is x squared. Another parabola with vertex at the origin. Here I have an absolute value function. Y is equal to the absolute value of x as the parent function, and that's a V-shaped graph centered at the origin. This middle one might be a little bit tricky, but it will help if we rewrite it as 1/2 x. X over 2, x divided by 2 is the same as 1/2 x. We can maybe see a little bit better that that is going to be a linear function. When I ignore that multiplying by 1/2, I'm left with just x. Or you can ignore the division by 2 and see that we're still left with just x. So this is yet again another linear function of the form y is equal to x. We have a line through the origin with a slope of 1. This is linear. Y equals x is the parent function. We have a line through the origin with a slope of 1. Absolute value. Y is equal to the absolute value of x. V-shaped graph centered at the origin. This is a quadratic. Remember, we need to focus on that highest exponent. So y equals x squared is the parent function. We have a parabola centered at the origin. And last, absolute value. Y is equal to the absolute value of x, which would be a V-shaped graph centered at the origin. Our next slide will now be to look at parent functions with some transformations applied. So I want to look at the parent function here, absolute value of x, and we can see that it's that V-shaped graph we expected. Our new function, g of x, has a transformation applied. The transformation is that we are subtracting 4 on the outside of the absolute value. Subtracting 4, if you notice, makes the graph a little bit different. It's now in a slightly different place. Instead of being centered at the origin, now it's centered at -4. So the graph was shifted down 4 units. It still has the same shape, it's just in a different place. In the second example, if I look at p of x, my parent function, it is still centered at the origin. My new function after a transformation is absolute value of x plus 1. we want to look at what that plus 1 is doing to our graph. If we compare it to p of x, we notice that the shape is the same. There's no stretches, it's not skinnier or wider. The only thing that's different is that it's in a different place. Specifically, it's 1 unit up from the original parent function. So subtracting 4 after the absolute value moved our graph down. Adding 1 to the end of the absolute value moved our graph up. So subtracting moved down, adding moved up. With quadratics, my parent function, y equals x squared, is centered at the origin, just like we'd expect. And then I have a new g of x function. This g of x function is x squared minus 5. And it did get cut off a little bit in the video, but this graph moved down 5. That vertex is now at negative 5. So because we subtracted 5 to the outside of the equation, we have the x squared and we just tacked on a negative 5. We're shifting the whole graph down 5. My parent function, y equals x squared, in that fourth one, is still centered at the origin. My new function is x squared plus 3. And the only difference here is that we shifted our graph up 3 units. Instead of the vertex being at the origin, now it is at the point 0, 3. So our conclusion here would be that adding and subtracting to the end of your equation is just going to move your graph up or down. We're now going to look at some horizontal movements. My parent function in this first graph is y equals x squared, and of course it's still centered at the origin, but my new function has been pushed 2 units to the left. What has caused this push in our graph, or the shift, is that we are adding 2 now inside with the x. Before, we had numbers added on after the x squared, but now the plus 2 is part of the x being squared with it, and that will cause our graph to shift left too. Our parent function, y equals x squared, is centered at the origin, and our new graph has been shifted to the right 3. So that right 3 movement came from the minus 3 inside with the x. Notice it's minus 3. Subtracting 3 caused our graph to shift to the right. In our last example, adding 2 caused our graph to shift left 2. So we're moving opposite. Not the same direction that you would think, but opposite. Here I have absolute value of x, and here I have absolute value of x minus 4 inside with the x. So if we're following the same pattern as before, my suspicion is that this minus 4 inside the absolute value with the x is going to move our graph horizontally, either left or right. Since it says minus 4, we should expect it to move in the opposite direction, or to the right 4. And sure enough, if we start at 0 and move to the right 4, we will obtain our new graph. In our fourth equation, I've got my parent function centered at the origin, and my new function g of x has a plus 5 inside the absolute value with x. I'm going to expect that to move my graph horizontally opposite what we would think. So I would expect it to move left 5. And sure enough, starting at 0 and moving left 5, we end up with our new graph. In conclusion then, adding a value to the outside or to the end of your equation is going to shift your graph vertically by k units. If k is positive, we go up, negative, we go down. Now here, this is saying that we are subtracting h, or we have the opposite of our h value, and it's inside with the input with your x value. That h value is going to shift your graph horizontally h units. We'll pick up the rest of this in our next video. Thanks for watching part 1.